Hello everyone. Uh, welcome to welcome to week extra week rather. Welcome to extra class on problem solving session of another communication. So we will today solve some problems which are not directly in the week lecture patterns. So they are like general questions regarding analog communication which are not necessarily covered in the NPTEL lectures, and we will be just solving a few. This will be a short class of 45-50 minutes. So we will be solving a few problems which are like generalized, more generalized problems, and then we will shift our focus to some concepts which have not been covered in the NPTEL class. So today's class is like that, extra class. So if you have any problems or any doubts, you can ask via mail or via the forum. Okay, so we'll start. Okay, so here we will be solving some gate level questions. Here we will be solving some gate level questions on analog communication. Okay, so we will be doing some previous year questions on analog communications, and to start, we will we will start with this 2025 gate paper. So consider a FM signal which is given as AC cos 2 pi fct plus 3 sin 2 pi f1t plus 4 sin 6 pi f1t. So here cos is the carrier. Because of the carrier there is a cos, and inside there is 2 pi fct which is the frequency term. Along with that there are two message signals, two message tones rather, not signals, two message tones. One is 3 sin 2 pi f1t and another is 4 sin 6 pi f1t. So the frequency is f1, and let us assume that fc is greater than 100 f. So what is the peak frequency deviation? So we will start with this. Okay. So here the message signal is given as AC cos 2 pi fct plus 3 sin 2 pi f1t plus 4 sin 6 pi f1t. So 3 sin 2 pi f1t plus 4 sin 6 pi f1t. 3 sin 2 pi f1t, and another message tone is 4 sin 6 pi f1t. So what is the maximum frequency deviation? So for frequency deviation, we have to, for this FM, for to calculate frequency deviation, we first have to calculate phase deviation. Phase deviation delta phi is given as 3 sine 2 pi f1t plus 4 sine 6 pi f1t. Now, maximum frequency deviation. Frequency deviation will be 1 by 2 pi of the rate of change of this phase deviation. So 1 by 2 pi ddt of 3 sine 2 pi f1t. So this will be 3 into 2 pi f1. Sine differentiation is cos 2 pi f1t plus 1 by 2 pi 4 into 6 pi f1 cos 6 pi f1t. So the maximum frequency deviation becomes 3, and this will cancel completely. So 3f1 cos 2 pi f1t plus 12f1 cos 6 pi f1t. So delta f will be delta f max. Now what will be delta f max? Delta f max will be reached when both of them are 1. When are both of them 1? Cos theta is 1 when theta is equal to n pi. So when 2 pi f1 t becomes n pi, then 6 pi f1t will also be n pi. So both of them will be integer. So at t equal to n by 2 f1, at t equal to n by 2 f1, where n is an integer, you will have both of them to be 1. So delta f max will be 3f1 plus 12f1. So it is 15f1. So the correct answer is 15f1. Correct answer is 15f1. Here you see fc is much greater than 100f1 is something that is given but is not used. So in GATE sometimes these kind of assumptions or these kind of redundant facts are given and you have to see through them. Next, we will go to second problem, where consider a message signal MT which is band limited to -W to W. Consider the following modulation scheme for the message signal. F DSBT is AC MT cos 2 pi FCT, and so there are two modulation schemes, one is DSBC and one is amplitude modulation. So there is a message signal MT which is band limited between -W to +W, and we have to take two different modulations of that. One is DSB and one is A. Now here AC and FC are amplitude and frequency of the carrier respectively. So in the case of A, mu denotes the modulation index. Now consider the following statements. Now consider the following statements. Consider the following statements. An envelope detector can be used for an envelope detector can be used for demodulation in the DSB-SC scheme if empty greater than 0 for all t. So envelope detector can be used to detect DSB-SC if empty is greater than 0. And another statement is that envelope detector can be used for in the AM scheme only if empty is greater than 0. So there basically you have to choose between only DSB-SC demodulation that envelope detector can only detect AM, and another is envelope detector can detect both AM and DSBs. So the options basically simplify to A, envelope detector works as demodulator for both AM and DSBSC. Next, envelope detector only works as demodulator for AM. These are the these are basically the two options. So each of the following is true. Now we know amplitude modulation AM can always be detected by this envelope detector. So our only task is to determine whether DSBSC can be DSBC. Okay. So in DSBSC, what we have to do is we have to just rather I am sorry for DSBSC we know that always we can have a envelope detector as a demodulator because what the envelope detector detects is the amplitude. That is the first thing. Envelope detector detects amplitude. So for DSBSC we can see ACMT cos 2 pi FCT. So message signal scaled by AC. Message signal is itself envelope. So of course it is a straightforward case of envelope detection. Next, so statement 1 is true. Next, for amplitude modulation AM scheme, for AM scheme we can always use demodulation. So if empty greater than 0 is an unnecessary condition, we can always detect modulation even if MT is less than 0. So 1 is true and 2 is false. Next, our amplitude modulator has output in volts as St equal to A cos 400 pi t plus B cos 360 pi t plus B cos 440 pi t. The carrier power is normalized to 1 ohm resistance is 50 watts. So the AM output is St equal to this A cos 400 pi t plus 360 pi t plus 440 pi t. We can see that this is basically the carrier. A cos 400 pi t is the carrier. This is the lower sideband. This is the upper sideband. So it is clearly given. So the ratio of total sideband power to the total power is 1 by 9. So here the okay. So here, sorry for the interruption. So here St is equal to A cos 400 pi t plus B cos 360 pi t plus B cos 440 pi t. So the message signal is given as A cos 400 pi t, the modulator signal, plus carrier signal, sorry, plus B 360 and B 440. Now this will lead to, now this is the carrier, this is the LSB, and this is the USB. Now total power, total sideband power in any of these tones, the power is a square by 2 or b square by 2, basically amplitude square by 2. So total sideband power is b square by 2 plus b square by 2, which is b square, and the ratio of the total sideband power to total power, and total power is a square plus b square. So this ratio b square total side band power by a square plus b square, it is given to be 1 by 9. It means 9b square is equal to a square plus b square. 2 root 2b plus minus 2 root 2b. Now the carrier power, so A is equal to 2 root 2b. So now the carrier power is given to be 50 watts. So A square by 2. Oh, sorry, this will be A square by 2. This is slightly wrong. 9b square equal to A square by 2 plus b square. So 8b square equal to A square by 2, or A equal to 16, A square equal to 16b square, or A equal to 4b. We are not interested in the sign, so we will not have any sign here. So A is equal to 4b. Next, A square by 2 is given to be 50 watts, as it is normalized to 1. So A equal to root 100. Root 100 is 31.62. So B is equal to 31.62 by 4. So this is approximately 32 by 4 or 8. No, it is 8. Now I want you to attempt uh, this question. Consider signal ST is equal to mt cos 2 pi fct plus m hat t. M hat t is the Hilbert transform of mt, which is phase shifted by minus pi by 2. M hat t sine 2 pi fct, where m hat t denotes Hilbert transform of mt, and the bandwidth of mt is very small compared to fc. So the signal st is A high pass signal, B low pass signal, C band pass signal. So what is this signal? Mt cos 2 pi fct plus m hat t sine 2 pi fct. So here we will go to a signal is given as st is equal to, for single sideband modulation, mt cos 2 pi fct plus m hat t sin 2 pi fct. Now, what will be SF? SF will be mf plus fc plus mf minus fc by 2, this one, and sine will do m hat f plus fc minus m hat f minus fc by 2j. Now we have to find the relation between m and n hat. So for that we have to find the Fourier transform of Hilbert transform. Fourier transform of Hilbert transform. So the Fourier transform of the Hilbert transform of a function is obtained by multiplying the Fourier transform minus j sigma omega. So it is basically multiplying by minus pi by 2. So minus j. So here we will do minus j. So this is minus j sigma omega. So m f plus fc plus m f minus fc by 2 minus j sigma omega sigma f by 2j m hat f plus fc minus j sigma f it's getting congested. So j sigma m f plus fc minus j sigma m f minus fc. So this one we can take j sigma f as common, is equal to m f plus fc plus mf minus fc by 2, j will cancel, so minus this 2 can be taken as common, minus sigma f. So if f is greater than 0, it is minus mf plus fc plus mf minus fc. So it will become mf minus fc if f is greater than 0. Similarly, if f is less than 0, it will become mf plus fc if f is less than 0. So that is the Fourier transform. It's either mf minus fc or mf plus fc. Now mt is a band pass signal, so it's just if mf is like this is mf. Whether it's mf minus fc or mf plus fc, it doesn't matter much. mf minus fc will be here, fc, and this is w minus w, this is plus w, and this is mf minus fc, and mf plus fc is advanced by fc, so it is here minus w w fc. So in both cases, this is band pass, this is also band pass. So either ways, the signal will always be band pass. So the correct answer is band pass. So option C. Let's take a 2 minute break.
हेलो बहुत पहले इंटरसिटी था ना 2 घंटा पहले बहुत पहले 2:30 बजे पहुंचता है हाँ हाँ क्या 2:30 बजे पहुंचता है हाँ बोल रहा 6 बजे चलेंगे कहाँ जाएंगे अच्छा क्यों टिक्का में प्रॉब्लम ये है कि बाहर का खाना और जंक्शन में जाएंगे तो एक हिसाब और कहाँ है टिकट पूरा बंद है लेकिन जो चाय दुकान सब बंद है आज तो सब वापस आ गए आज अक्का आईआईटी वापस आ गया है क्या भीड़ था स्टेशन पूरा आईआईटी वापस आ गया है आज इंटरसिटी आधा आईआईटी के स्टूडेंट से ही भरा था हर में आधा खाली हो गया बहुत स्टूडेंट्स थे फोटो में मिल रहा था और कहीं तो है नहीं ओ बाहर अच्छा 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 टिक्का का वो ये क्या खुला है वो नीचे वाला ग्राउंड फ्लोर वाला एरिया वो ग्राउंड फ्लोर वाला जो कॉमन ईटिंग एरिया है ना वो अच्छा अच्छा, चाय मिल रहा है लेकिन वो ईटिंग एरिया खुला है ना, बैठ के खा सकते हैं ना। ठीक, हाँ, फिर उधर कहीं कुछ भी लाके खा सकते हैं। हाँ उधर, हाँ या हाँ एग्जैक्टली ग्राउंड फ्लोर में खाते हैं। हाँ वो तो कॉमन ईटिंग एरिया है, उधर कुछ भी खा सकते हैं। ठीक, मैं फिर 6 बजे, 6 बजे। ठीक है, ठीक है, हाँ हाँ, ठीक। बल्ली मना।
Okay. So for the next question, consider an FM signal ft is equal to cos 2 pi fct plus beta 1 sin 2 pi f1t. So there are two message tones, beta 1 sin 2 pi f1t and beta 2 sin 2 pi f2t. So this is very similar to the question we have done previously. So it will be beta 1 f1 plus beta 2 f2. So this we have done previously. So I am not repeating this. Okay. Next, consider an angle modulated signal xt is equal to 6 cos 2 pi into 10 to the power 60 plus 2 sin 8000 pi t plus 4 cos 8000 pi t. So here there is the angle modulation. So what is the power of xt? Now for phase modulation or frequency modulation, the power is not affected. The power only depends on amplitude. That is something that needs to be committed to the mind, that power only depends on amplitude. It does not depend on frequency, it does not depend on phase. So FM signal power is equal to carrier power always. Now with that done, the carrier power is 6 square 36, 6 square 36 by 2. So 6 square 36 by 2, 18 watts. So the correct answer is 18 watts. Next, which of the following require analog modulation scheme requires minimum transmitted power and minimum channel bandwidth? So single sideband, because VSB uses, VSB means VSB means some 1 plus eta sidebands. Vestigial sideband, VSB is vestigial sideband modulation, so it has 1 plus eta sidebands. So one whole sideband, and eta is a fraction, eta is 0 less than 1, so eta is a fraction, so 1 plus a fraction of sideband. So one whole sideband and a fractional sideband is VSB. It is somewhere in between DSB and SSB. So by bandwidth requirement, we can say DSB is greater than VSB is greater than SSB. So it is SSB which requires the least amount of bandwidth. Next, an AM signal and a narrowband FM signal with identical carriers, modulating signals and modulation indices are added together. So this one is a bit complicated. So there is a AM signal and there is a narrowband FM signal. So a narrowband FM signal means the frequency deviation is much less than the carrier frequency. So for a narrowband frequency signal modulation, NBFM frequency domain representation, there will be one, just like DSB, there will be one carrier and one two sidebands, just like DSB. See here. So NBFM will have a carrier, a DAL upper sideband, and an inverted lower sideband. Whereas AM will have carrier, upper sideband, and lower sideband. So here AM frequency spectrum looks like this. There is a carrier at FC, there is this, and there is this. So it is AM. So there is a lower sideband, there is a upper sideband, and there is a carrier. Now we will shift our focus to NBFM. Now if you do work out the frequency domain representation of a narrowband frequency modulation, it has one FC minus FM, and then there is a carrier, and then there is FC plus FM. So if you add these two, if you add these two, add these two, you will get a carrier and upper sideband, but the carrier will be 2 AC, and there will be a upper sideband. It will be also be double, so AC by 4 it will become AC by 2, ACAM by 4, sorry, ACAM by 4, this will become ACAM by 2, but this and this will cancel, so there will be no lower sideband, so it will only have a single sideband. So what it becomes eventually, it becomes single side band modulation. So we can say that, or SSB. So we can say NBFM, provided they are of same specifications, NBFM plus AM, same specs, same specification, they have to be, will give rise to SSB. So NBFM plus AM will give rise to SSB, provided they have the same specifications. So it is SSB with carrier. Okay, uh, so that will take us to the end of the problem solving session for analog communications. We solved some from previous year question of GATE, and we will look forward to solving the NPTEL week wise problems from the next class. So we have 2 more weeks left, week 11 and week 12. Week 11 will be this Tuesday, next Tuesday will be week 12. Thank you and have a nice day.